All right, so we have a couple limits that we want to evaluate, not necessarily having to do with the derivatives or anything, but just some more techniques in evaluating these limits. And we will do many more things with the derivative. But right now we want to look at some different ways that we can evaluate our limit. And so without using the graph or the table on this problem, we want to just evaluate this by using some of the algebra skills that we have to simplify our input. Because if I try direct substitution first, which is always, remember, that's always the first thing you want to do is try your direct substitution. You'll notice that you have 0 over 0. And whenever we have 0 over 0, that suggests that there is a removable discontinuity. So something that looks like a hole. And usually if you have a removable discontinuity, you can factor. If you have a hole, you can factor and cancel things. Now here it looks a little difficult to factor either the numerator or the denominator. The denominator is prime, it's just x. The numerator doesn't really look like there's anything in common, so factoring doesn't seem super easy or super helpful, but we still know that we have that 0 over 0. So there's something that can be done. And so what we should do right now is we should multiply by a conjugate. So typically when we have a square root, specifically when we have a square root in the denominator, we multiply by the conjugate, or we multiply by itself in order to remove the square root in the denominator. We want to rationalize the denominator. What we're doing right now is we have this issue of I want to evaluate at 0, so I have this denominator that's going to cause me the issue. So what I want to do is I want to rationalize the numerator, make my numerator a little nicer, my denominator a little uglier, so that I can do a direct substitution that it works. So what we're going to do is I'm going to keep the limit notation. I'm not allowed to drop that yet, but I'm going to take my original function I'm doing the limit of, and I am going to multiply by the conjugate of the numerator, so the square root of x plus 1 in both the numerator and the denominator. Remember, I don't want to change my function. I don't want to change the value. I want to keep it the same, so we're going to multiply by a 1. That red fraction is 1. So we're not altering my function, I'm just changing the way it looks. And so by doing that, and again, I have to keep that limit notation the entire time until I actually evaluate the limit. And I know it's frustrating and I know it's annoying, but you cannot drop the limit notation, not until you actually evaluate. But when I do this, when I multiply out my numerator, I end up getting x plus 1 minus 1. And you can go through all of those steps, but you may recall from Algebra 2, multiplying by conjugates, a minus b times a plus b gives you a squared minus b squared. So if you remember that, you can use that shortcut, but you can go through the process of actually multiplying everything out. My denominator, I'm just going to write it this way. It's x times parentheses x plus 1 plus 1. And I'm going to keep simplifying because now I can combine some things in the numerator. And I end up with x over x times the square root of x plus 1 plus 1. And now you can see, oh, there is a removable factor. There is a factor that I can cancel. This x in the numerator and that x in the denominator, those cancel. So now my limit is as x goes to 0 of 1 over the square root of x plus 1 plus 1. And now evaluating my limit by direct substitution, I could drop my limit notation because I'm actually going to evaluate it now. I have the 1 over the square root of 1 plus 1, or 1/2. So this is using what we know about conjugates and their relationship to each other to rationalize the numerator this time, make the numerator nicer and the denominator a little bit uglier, so that we can evaluate by direct substitution. Okay, so typically if you have something that involves a square root, a conjugate might be something helpful, something that you can use to simplify your limits. All right, we have a couple more examples we're going to do. This one right here, the directions are slightly different. It says we're going to approximate the limit. And typically when you see approximate, that indicates that you're probably going to have to use either a table or a graph to help you. And you can sort of see with this function why you might need to do that. Again, if I try direct substitution first, sine of 0 is 0 over 0 tells me this suggests a removable discontinuity again. It suggests that there is a whole removable. Is there an E? How did I write it before? Nope, okay. This suggests that there is a hole on our graph, but just like before, looking at this initially, it doesn't look like it's going to be factorable or be something nice. But unlike the one we just did, there's no square root to do a conjugate. There's nothing really I can algebraically do, at least with what we know at this point in our mathematical careers. There's nothing that we can do to sort of simplify this. This actual limit, you might see if you take Calc 2, you'll see this, and you'll see how we can write sine in a different way, and that you can do some factoring then and cancel, but we're not going to get into that. So what we're going to do is we're going to look at the graph. Okay, we're going to look at our graph to help us. So I'm going to use Desmos. You can use your graphing calculator if you want. But when I graph it, and knowing that this is a 0 over 0, that there's a hole there, if I look at my graph, I can see, I've got this sort of super compressed. The further out I go from the origin, the more my function looks like a line. It is always doing this wave motion. It's just the amplitude as I go further and further out just gets smaller and smaller and smaller, which should make sense because this is a 1 over x multiplied by our sine of x. Okay, but if I'm looking at the center of this graph, when my x is equal to 0, you can see that it's following your typical path for it to hit at 1, but it doesn't actually hit at 1. There is a hole there. And when you look on a graph, you actually don't see the hole because it's so tiny. It's infinitesimally small, but it is actually a hole there. It doesn't actually exist at x equals 0. But graphically, we can see that as I come from the left and as I come from the right, that I am approaching 1. So if I go back here using my graph, I can say that the limit here is 1. And we use our graph to approximate that. So that phrase right there, approximate the limit, is typically a good indicator. You should try a table or graph. Now, these two limits here, you'll notice that the notation is slightly different. And again, it does say to approximate the limit, so that means direct substitution probably won't work. We still might want to try it first, but it probably won't work. But if you look at your limits, the function is the same for both of them, and they're both approaching 0. X is approaching 0 on both limits, but this first one has this little negative sign in the top right corner next to the 0, and the second one has a little plus sign. Those two little symbols are talking about, okay, this is a one-sided limit. When we first mentioned limits and we first were talking about them, we said one way that your limit might not exist is when you approach from the left and you approach from the right, you approach different values. We said if you're approaching from both sides and you approach different values, your limit doesn't exist. A one-sided limit says, okay, let's not come at it from both sides, but rather let's just come from one side or the other. So this first limit, this is what we would call a left-hand limit. This right here says I only care what value I'm approaching from the left side. So the little negative, we use that to help us because on a number line, if you're on the left-hand side of 0, you're in your negative. So if I'm approaching 0 from the left, I'm looking at -3, -2, -1, all the way until I get to 0 from the left side. The second one is what we would call a right-handed limit. And we use the positive symbol to denote that we're coming from the right-hand side. And it doesn't have to be you're approaching 0. You can approach 2 from the left or from the right. We still use negative for the left and that plus sign for the right. All right, so when you have a left or right-handed limit, unless your function is written as a piecewise function, your easiest way to evaluate your limit is going to be using a graph. So that's what we're going to do right now. So I have Desmos again. I've got these two graphed. Got this function graphed. Got to zoom out just a little bit for us. All right. So we looked at one similar to this graph the other day. We looked at the function, the absolute value of x over x. So we've just multiplied the numerator. We've multiplied the x in the absolute value by a factor of 2. So we have 2 times, or the absolute value of 2x over x. And if I want to start with my left-hand limit, I'm going to start on the left side of my my value I'm approaching. So we're approaching 0. So when I start from the left and we're approaching 0, oops, we're going to look on the bottom green line. And notice how the y values don't ever change. So they're approaching a nice number for us to evaluate. We're approaching -2. My y value, at -4 is -2. At -2, it's -2. At -1, it's -2. At 0, it's an open circle. So 0, remember, if I substitute in, I get 0 over 0. That doesn't work. But you can tell that I am approaching the value of y equals -2 from the left. So you can say, well, the limit from the left is -2. When I look at the limit on the right-hand side, going back to Desmos again, I'm going to look at the line on the top. And looking at the line on the top, you can see all the y values as I come from the right-hand side. So starting at x equals 4, and then x equals 2, and then x equals 1. All those y values are positive 2. Until I get to x equals 0, which again, open circle, it doesn't exist there, but my y value is approaching positive 2. So my right-handed limit is positive 2. And looking at these two, if we were just asked, if someone came along and said, well, what's the limit? Well, let's write an M there for limit. As x approaches 0, no positive or negative of the absolute value of 2x over x, we would say this does not exist because the limit from the left and the limit from the right don't match. But the individual single-sided limits do exist. And so that idea of the left-handed limit and the right-handed limit not existing or not equaling the same value, so the whole limit does not exist, is very much connected with continuity. And we'll talk about more about continuity in our next meeting. But the definition of a continuous function, all right, the formal definition for a continuous function says a function is continuous at a value or a point C, so an x value for C. If my function exists, so that's the first thing, my function needs to exist there, in the limit from the right and the limit from the left of the function at that value C. So as I approach from the right side and from the left side, they need to be not only equal to each other, but they also need to equal the function value. All right, and we'll talk about this more later, but there is a video. It's at this link right here, um, which I'm going to show right now, but you can look at that again later, which has more of a conceptual understanding of continuity. This is our formal definition, and this is what you're going to use in calculus. But to get a better understanding of continuity, we have this little video. Our function f of x equals 1 over x, which we see is graphed here with the, remember we have that vertical asymptote along that y-axis. And we're going to start with what we already finished. We're going to look at that difference quotient. So we just a couple minutes ago evaluated and simplified our difference quotient for our function. And we ended up with -1 over x squared plus x times h. All right, so we want to quickly talk about what does this represent. So think back to, we just talked about this. We had that secant line slope, and we wanted to make that secant line get closer and closer to becoming the tangent line so that their slopes were the same. And we found our secant line slope by looking at the rise and run between 2 points along our graph. And when we evaluated those, when we did our rise over run, we ended up with our difference quotient. So this right here, this -1 over x squared plus x times h, this will represent the slope for any secant line connecting 2 points on our graph of our function f of x equals 1 over x. So if I say I had another point right up here and I connected those two with a secant line, I could find their slope by using this -1 over x squared plus x times h. All right, now we want to use our definition of our derivative to find f prime. Remember, f prime is the label we give to our derivative. So using the limit definition, we have, okay, well, f prime is equal to the limit of our difference quotient as h goes to 0. So we let h get closer and closer and closer to 0. We evaluate that limit of our difference quotient. We find our derivative. So in our case, we're going to do all the work. We just take all the work we did before. We're going to substitute in our simplified difference quotient, -1 over x squared plus x times h. And now we're saying, okay, we want the limit as h goes to 0 of the function -1 over x squared plus x times h. And so we try our direct substitution. This time direct substitution works, and we end up with -1 over x squared. So we can say our limit f prime of x equals -1 over x squared. That's my derivative. That's the derivative of our function 1 over x. And so we could use that and substitute in any value for x that I want, and I can find my instantaneous rate of change. I can find the slope of my tangent line. The slope of my tangent line at a specific point. So what we're going to do right now is we are going to find the slope of the tangent line at this point labeled A. And then we're going to use that to write the equation of our tangent line at that point labeled A. So at that point labeled A, I'm going to find my tangent line equation. Now that is at x equals 2. And I know, I'm drawing it, and it looks like this. This is my line tangent to my function at that point, A. What we want to do is we want to find our line equation. So think back to Algebra 1. You've got line equations. You need to write the equation of a line. You need to know 2 pieces of information. You need to know a point, and you need to know your slope. Now, our point we're going to get by saying, well, if I know my x value on my function, my y value on my function, that's going to be the y value for that point because this is a tangent line. They share that point in common. So I'm going to start by just saying, okay, if I want to know this coordinate point right here at A, well, x is equal to 2. We know that. That means my y value using the function, the original function f of x, is going to be 1/2 or 0.5. So these two values right here, these are going to give me my x and y values for my coordinate point that the line is passing through. My derivative, Remember, the derivative is the instantaneous rate of change or the slope of the tangent line. So I'm going to use the derivatives equation to find my tangent slope. So I'm going to take my x value too, and I'm going to substitute it into my derivative. That gives me my slope at the x value of 2 as negative 1/4. So then I can write a line equation, and we're going to label the line equation g of x as saying, well, this is going to be m times x minus h plus k, and I get negative 1/4 times x minus my x value from my coordinate point 2 plus the y value from my coordinate point 1/2 or 0.5. And by distributing the negative 1/2 and adding and combining like terms, I get my tangent line equation as negative 1/4 x plus 1. And that's in my y equals mx plus b format. So we used our original function to find the output, the y value for our coordinate point. So we knew the x value because we have to know what point I'm going to do my derivative at, that my tangent is going to be intersecting my function at. So we said we want the tangent line when x is equal to 2. So I know my x value is 2. We need to find the y value at that point. So we use the original function for that. And then to write any sort of line, I need to know my slope. The derivative gives me my slope. So negative 1 over 2 squared gives me the negative 1/4 for the slope of my tangent line. All right, we're going to go back to some more practice evaluating some limits, looking at some left-handed and right-handed limits, and seeing some other algebraic tips and tricks that we can do to simplify things. Something in our sketch pad, like this function, this parabola here, and we used it to help develop our limit definition of a derivative. All right, so we had this limit right here, and we had the difference quotient, and we said, okay, you take your difference quotient, f of x minus h, or excuse me, f of x plus h minus f of x divided by h, and if you let the limit go to 0, that's going to be our derivative. All right, it's the same thing as the slope of our tangent line, because what we're doing is, remember, we were taking that secant line and we were taking our tangent line and we were letting that second point get closer and closer and closer. So we were letting that distance in the run, the difference in the run there, get smaller and smaller and smaller. And if you actually let it be 0, then your secant line is your tangent line, and that's what we're trying to find here. However, based off of, the slope that we get for our secant line here, we have our denominator is just h. So if my run is just h, I can't actually let that go to 0. And so this is why we don't actually have h go to 0, but rather we look at the limit as h gets infinitesimally close to 0. So think of the smallest number you can think of, the one that's closest to 0, and then make it even closer. So you've got, 0.00000000001. You can make it even closer. And so that's what our limit allows us to do. Our limit allows us to evaluate the slope of the secant line where my run is 0, essentially, where that h value is 0. And that's going to give me the slope of that tangent line. And remember, we talked about the other day how the slope of our tangent line is that instantaneous rate of change at one given point. And your instantaneous rate of change is our derivative. So that gets us this idea right here. Our derivative, our f prime of x, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Or our derivative is equal to the limit of our difference quotient. All right, so that's one of those, that's the main reason we've been doing these difference quotients all year long, is because we were looking at the limit. Or we wanted to build up to taking the limit of it so we could find the derivative. So we have this right here, our function. We looked at a slightly easier one last time where we had just x squared plus 1, but we can do the same thing here if we want. We can find the limit of our difference quotient as h goes to 0 for this particular function. We're not going to do that. What we are going to do actually is we're going to look at the limit of the difference quotient. So finding the derivative of the function we just evaluated the difference quotient of. Today we are continuing our discussion in Chapter 12, Section 2, Limits, and the limit definition of a derivative. Before we get too far into that, we're just going to do this difference quotient here. We're going to evaluate and simplify the difference quotient for our function f of x equals 1 over x. So if you want to give this one a try, you can pause the video and then come back and see how you did. All right, so we want to simplify our difference quotient here. So we're going to start by evaluating f of x plus h minus f of x over h. For our function, f of x plus h is going to be 1 over x plus h minus f of x minus 1 over x for us, all over h. So what we've done is we've substituted. Now we need to simplify. And you might be looking at this and being like, how in the world do we simplify? I would start, and almost anytime you have something like this, start with trying to combine those two fractions, those two rational expressions in your numerator. And so we do that by getting a common denominator. So we end up with x over x times x plus h minus x plus h over x times x plus h, all divided by h, or x minus h, and remember I'm just distributing that negative right there, all over x times x plus h, all of that over h, which gives me negative h over x times x plus h over h. And I'm actually at this point going to write the h in the denominator as h over 1. So I can do my copy dot flop. So I have negative h over x times x plus h times 1 over h. H and h cancel. So now I have negative 1 over x times x plus h. And simplify, you could stop here. I'm actually going to distribute the x in the denominator. So we have our simplified difference quotient is negative 1 divided by x squared plus x times h. And we're going to hold on to this idea. We're going to come back to it in a couple minutes, and we're going to look at actually the derivative of this function using the fact that we've already found and simplified the difference quotient.
In this land of many mysteries, it's a strange fact that the largest legends seem to collect around the smallest creatures. One of these is a mousy little rodent called the lemming. Here's an actual living legend, for it's said of this tiny animal that it commits mass suicide by rushing into the sea in droves. The story is one of the persistent tales of the Arctic, and as often happens in man's nature lore, it's a story both true and false, as we shall see in a moment. Ahead lies the Arctic shore, and beyond, the sea. And still the little animals surge forward. Their frenzy takes them tumbling down the terraced cliffs, creating tiny avalanches of sliding soil and rocks, and seemingly indestructible lemmings. The final precipice. This is the last chance to turn back. Yet over they go, casting themselves bodily out into space. All seem to survive the ordeal, for now they begin to swim. Not toward land, strangely, but away from shore, toward the far horizon. Others find the beaches by roundabout ways, when they too plunge into the waves. It's not given to man to understand all of nature's mysteries, but as nearly as he can surmise, it would appear that the lemmings consider this body of water just another lake. And if it's a lake, then it must have a farther shore. And so they strike out boldly. But gradually strength wanes, determination ebbs away, and soon the Arctic Sea is dotted with tiny bobbing bodies. And so is acted out the legend of mass suicide and destruction of a species, it would seem to be, except that nature, in her infinite wisdom, has spared a few. Back on the Arctic plain, there remains the small handful that did not make this fatal journey. And in time, new generations will take the place of those that have been lost. And yet, when the population cycle mounts to another peak, the lemming legend will be told again, and will come to this same amazing climax, a final rendezvous with destiny and with death.